Good morning, everyone. Thanks for taking the time and joining us. And thank you, Steve, for accepting our invitation. So, Steve Margulis is a professor at the Department of Civil and Environmental Engineering. Steve did his undergraduate degree in University of Southern California and the graduate degree in MIT on hydrology. And when I came to the United States and I started my PhD, I became very much interested on his research. I read his paper. I didn't know him personally, but I was always fascinated by about what he does. So thanks, Steve, for accepting our invitation. Steve is currently serving as the department head at UCLA, and I think among the awards that he received, as far as I remember, because I used to track your success in academic environment, but he has NSF Career and NASA Early Career Awards, both in his portfolio of awards, if I'm not mistaken. Without any further ado, thanks for coming to the University of Minnesota, and the floor is yours. Thank you so much.
Great, thank you very much, Ardeshir. It's a pleasure to be here. This is my first trip to University of Minnesota, and it's been a wonderful experience. I got to walk around yesterday in some very nice weather. I was a little worried about it. Despite studying snow a lot, I spend most of my time in Los Angeles, which is a very different kind of climate. So let me just get started here. So I'll just give a quick background just for context for some grad students. Try to motivate the problem, why snow is important, what some of the gaps are in studying snow. And when I say snow, I'm talking about snow on the ground, kind of water stored on the ground as snow. Some of the approaches we've taken to trying to solve some of these problems. And then the talk is mainly going to have two parts. One is work we've been doing for a longer period of time to develop some new data sets. And the other is a more recent, where I was tasked with leading developing a snow mission concept, a NASA proposal. So I'll talk a little bit about that, which was an interesting experience, and then kind of wrap up with some conclusions and future work. So here's my background. I don't want to spend a lot of time on it, but for grad students out there, I often hear, oh, they're very worried about what choice of topic their PhD is. I just want to put this up here in that I studied absolutely nothing about snow as a grad student. Never thought about snow until I got to UCLA, which is weird because it never snows there. But water resources in the Western US are very much snow dominated. And so it became very clear I better start worrying about snow once I got there. So our topics have evolved to kind of some of the warm season processes that I studied as a grad student, including remote sensing, but mostly of soil moisture, to remote sensing and data assimilation of snow processes. So very roughly, if you kind of group some of the things we've been doing since I got to UCLA, there's kind of three topics. I'm going to focus today on these last two, just in the interest of time. And largely the motivation here is, and for context, I'll mention it later, there's never been a kind of optimized snow water equivalent mission launched. And so as a snow hydrologist, we've been spending the last 34 years trying to take the data we do have, which is suboptimal in many ways, and trying to estimate snow processes. So that's what's really motivated these first two boxes. I'm going to focus on the second one, which is kind of an area that's been more successful, frankly, using a long-term record of fractional snow-covered area data that does exist to estimate snow water equivalent. And then more recently, again, I've been working on the process of developing a new mission that is more optimized for this goal of estimating global mountain snow water equivalent. These are all evolving, but I'll just kind of touch on the key aspects of this. So the first importance of snow, not just snow, but most of what I'm going to be talking about is mountain snow and its importance. And just as a quick motivation, if you ask where is snow important, it's a very loaded question. So I'm saying for humans, and by that I really mean for water supply purposes for humans. So this is a model-based result, and any global model-based result related to snow, you should probably take with a grain of salt. So I'm just using this as a mask to say everywhere in light blue is where at least 20% of the annual runoff comes from snowmelt. So this is an area where snow contributes a significant amount to the water cycle in that area. If you, in contrast, look at where do humans kind of need water, so this is, again, just a mask of global regions where a significant amount of the annual freshwater runoff is used for things like irrigation, industrial and domestic uses. You see there's almost an incoherence here, right? Snow at high latitudes, lots of water use at mostly mid latitudes, and this is mainly almost a population density map. But if you look at the overlap, where do these two things kind of coincide? You get a map like this, where the dark blue areas are really the domain of interest in our work. So the dark blue areas are those areas where the gold areas where water use is a significant amount is coming from snow, has snow in its upstream areas. And if you kind of squint or understand the geography, these are mostly what we call the water towers of the globe. So Western US, high mountain Asia, Alps, Andes, these are areas where there's large populations downstream of mountains. And as a result, we've built a lot of infrastructure to plug into that kind of virtual reservoir that sits there during the winter and then melts in the spring. And so the overarching goal here for our work is, could we estimate snow mass, snow water in these dark blue areas on all of the useful timescales, seasonally, subseasonally, interannually, and so on. Okay, so that's kind of the motivation. So the challenging part is, how do we do that? And so I put this picture here just to kind of give you a mental picture of how heterogeneous this domain that we're talking about is. And it's a huge challenge to estimate snow. And so specifically, the variable I'll be using over and over again is SWE. If you're not familiar with that, that is snow water equivalent. That is, if you took the amount of water on the landscape and melted it, how much water would that yield? And so for a water resource planner, this is the key variable. It tells you how much water is here, and therefore likely how much is to melt. And we can then fill our reservoirs, irrigate our agriculture, and so on. So how do we characterize this? One way, of course, is in situ measurements. And so this is a map of what's called the SNOTEL network over the Western US. This is kind of the gold standard. Hardly anywhere in the world, except maybe in parts of the Alps or other few places, do you have this density of measurements. The misleading part is how big I choose to make these dots can be very misleading to how dense this network actually is, right? So if you kind of do the math here, kind of at elevations where snow starts to become pretty persistent, this so-called dense network has about one station for every 1,300 square kilometers. So this is not a very representative or optimized network. It's largely driven by practical aspects of how do we install this in a place we can access and maintain and so on. But this is very important in the Western US. What this is typically used, if you follow these things, is they're used to track, what percent of normal is the current water state in these mountains. Of course, the notion of normal is changing, right? So as climate is changing, the regression models that have been developed over the years are becoming less reliable. These measurements tend to occur at kind of mid elevations, largely for accessibility reasons. That's where we can get to. So snow above those are often undersampled, as well as in areas of higher slopes and forest. And there's kind of a famous example in 2015, which was a very, very dry year. There's a famous picture of the governor going to this kind of sampling station that's a pretty famous one for forecasting water, and there's zero snow. And so regression forecast models using that data is going to predict there's no snow available, right? Even though it was a dry year, there was snow above the measurement elevations. And so there's clearly a gap in our knowledge. And then as you move away from the Western US, this dense data set goes away largely. And so the real question is, how do we do better? And so remote sensing is the obvious answer in terms of mapping this heterogeneous variable. The problem is, and this is a famous quote in kind of a water resources research review of remote sensing and hydrology, in that SWE, snow water equivalent, is kind of this holy grail that we haven't really figured out how to remotely sense well. Okay, and so a lot of what has been done over the last 20, 30 years is taking measurements which are suboptimal and trying to estimate this variable of interest, snow water equivalent. Okay. Snow is an interesting one in that the measurement of snow-covered area using visible wavelengths is one of the true success stories of land surface remote sensing, right? So in this picture, we see very clearly snow has a signal. It's very bright in the visible. And so we have long records of snow-covered area estimates. but that is not what we're interested in from a water resources perspective, which is what we need SWE. There's never been a dedicated SWE satellite mission. So most of the retrieval algorithms that are out there are opportunistic. We take something that was designed to measure something about the atmosphere and try to use that data, or something that's measuring vegetation, and we try to use that to learn something about snow, but it's a very suboptimal process. And snow is a very complex medium. So there's lots of so-called confounding factors. The fact that it's a layered media, grain size can cause havoc in the microwave response. If the snow is dry versus wet, it can have a totally different signature, and forest can obscure snow that is underneath it. Okay, so what does this mean? It means that most of our estimates of what's happening kind of in global scales for snow water equivalent is model-based. So the obvious question is, how well do models do? And I'll kind of come back to this picture based on the data set we've been developing. So this is just a suite of globally available models. These are mostly land surface models, which have a snow component built in, that are forced with best estimates of precipitation, air temperature, and so on. Okay, and so if you squint, you see there's some coherence among these different models. And this is, I should say, just the peak SWE climatology map. So if you take a 30-year period and take the average amount of maximum SWE, this is what you get across these different models. It's not hard to see that these yield quite a bit of difference. And so this is just shown in a bar plot form. What if you were to integrate over the Western US domain for all of these models, how much snow is stored in these mountains in cubic kilometers? And you see there's a very large variability. So across the models, it's about 150 cubic kilometers, but the standard deviation is about 85 cubic kilometers. So something we don't know certainly very well. So the uncertainty is high. The other question is, which of these is correct, right? We'd like some reference data sets to try to say, which of these is correct? Why are certain ones incorrect, and so on. And so we need an observationally constrained set of estimates. So that leads to what we've been doing over the last 10 to 15 years or so. We've been using data assimilation as kind of our framework. If you're not familiar with that, it's really just a Bayesian estimation approach. So in this one slide, I'm just going to try to highlight the keywords without really doing any of the math. So this Bayesian estimation is a framework that allows you to merge measurements and models, kind of loosely speaking. Provides a rigorous way of doing that. Measurements are key. In this context, we're mainly talking about remote sensing measurements. And they're treated as random variables. So we are recognizing from the start that these remote sensing measurements have measurement error. And almost always, they're indirectly related to what we're interested in, right? So the example I'm going to use in a minute is, we have a measurement of snow-covered area, fractional snow-covered area. We want SWE, right? So we're going to use we're going to need to transform across the measurement and state space. So how do we kind of start to do that? We usually use physically based models. And so in a Bayesian framework, you've got prior estimates and posterior estimates. Prior estimates are usually your best guess of what's happening. And the way we typically do that is we use a model. So we give it our best precipitation, our best air temperature to kind of come up with what we think is a best estimate. Also treating those estimates as a random variable, where we're acknowledging all of the sometimes very large uncertainties in those estimates. Okay, and another key aspect of Bayesian approaches is that it recognizes these uncertainties, propagates them so that your final estimate, which is the so-called posterior estimate, which involves essentially Bayes' rule, itself gives you a distributional estimate, mean and say standard deviation. And there's lots of varieties of how you implement this. I'm not going to get into those details too much. One word I'll use is reanalysis. Sometimes these data assimilation frameworks, the end result, the posterior estimate, is called a reanalysis, where you can think of almost as the model as your first analysis, and then you're doing a reanalysis in terms of integrating measurements. Okay, so that's all kind of motivating the problem and the tools that we are going to use. And so in part one, I'm focusing on, can we take the data that we do have, as suboptimal as it may be, from visible near infrared measurements using what we call fractional snow covered area. So these are maps of, for a given grid cell, how much of that is covered by snow. We can do that reasonably well. Can we use that to estimate snow water equivalent? And so what I want to start with is why data assimilation is a very attractive way of doing this. So in kind of your traditional NASA framework, what ideally is happening is you use what's called a retrieval algorithm, where you could plot, a scatter plot of what you're measuring versus what you're interested in. It has a beautiful correlation with very low uncertainty bars. Some variables work that way. Many and most in snow do not. And so I want to kind of motivate that. So this is just a representative example. You'll see this in the estimation framework I'll talk about in a second. But just imagine this is kind of the two variables we're focusing on: snow water equivalent as a function of time, snow covered area as a function of time over one water year, or one seasonal cycle. So we start with no snow. We have snowfall, snow accumulates, snow melts. And then this is the fractional snow covered area. So one problem with snow covered area is that it saturates. So usually once you get a certain amount of snowfall, a grid cell will be fully covered in snow. It might have 4 inches of snow. It might have 4 feet of snow. That's hard to distinguish. And what we're most interested often is the peak snow water equivalent. So if you're a water resources manager, that's telling you how much water will likely run off, or at least a upper bound on that. And we see that during that time, there's essentially no signal in fractional snow covered area. The sensitivity of snow covered area to sweep changes is 0. So that's very bad for a retrieval type of approach. And this is just another way of putting that. So if you take an instantaneous snapshot of snow covered area in SWE, you get a relationship that looks something like this. There's certainly some increasing behavior of SWE versus snow covered area, but it's a bit of a noisy mess. So retrieval is not a very useful approach in this context. And this is well known. So most folks in snow study visible and focus on snow covered area, or study microwave and focus on SWE. Here we're trying to bring those two together. So how do we do that? So again, we're going to rely on estimation via data assimilation. And so what's the magic? And there is really no magic. It's just trying to pose the problem in a way that integrates information. So I'm doing this relatively schematically. Snow, you can just apply mass balance to it. And this is one simple way of doing it, saying that SWE changes are really mostly the result of precipitation in the form of snowfall and melt. So M here is snow melt. So we can model that, and it's certainly more complicated than that, but this is the rough idea. And if you just kind of rearrange this a bit, the SWE at any time, here I'm just writing it as peak, you can think of over the ablation season, that's essentially the melt season. You could essentially back out how much SWE there must have been if you knew what the melt signature was over time. Okay, it turns out that melt is a function of two things, kind of a grid average melt flux, which you can calculate with the model, and the fraction of snow covered area. So that's where you can start to see a connection between SWE and snow covered area if you have this kind of information. But to do that, you need a model. And so this is where we can start to bring the data assimilation approach together, where we take a model to get a prior estimate and integrate that relationship and estimate SWE in this context from snow covered area. So we have a time series of snow covered area measurements, specifically in the ablation season, and we're going to use that to back out how much snow water equivalent there must be. I should say, feel free to interrupt with questions if you have any. Otherwise, I can certainly answer at the end. So there's a lot going on here, and there's a lot of work that went into this, but this is kind of the pretty picture version of the framework that we developed over several years and several different components. Again, I don't want to go through all the details. The simplest way to think about this is the red boxes are the modeling part of the framework, along with the uncertainty. So there's many, many people working on many, many useful data sets, like meteorological data sets, land surface characteristics, DEMs, land cover, and so on, all of which has some relationship to either how much snow will accumulate or melt. And so we want to integrate that. So how do we do that? We have to use a physically based model, or a model, I should say. And so these red boxes, when you put them all together, land here with our prior estimate. So this is our kind of best guess estimate for how much SWE there is and how much snow covered area there is over a seasonal cycle. The blue boxes are the integration of measurements. So if we take fractional snow covered measurements over time and use essentially Bayes' rule to integrate that into our update or reanalysis step, we can get our posterior estimates of SWE and snow-covered area. Okay, so just to kind of illustrate this schematically, let me just show you how this works. And again, this is being done at kind of every grid cell that we have measurements and model estimates for. So kind of taking this through the red boxes, what we get is an estimate that looks something like this. This is our prior estimate, and the dark red line is our mean estimate, and then the shaded region is kind of the uncertainty bounds. Just to illustrate the fact that we're trying to integrate all of the uncertainty that goes into these estimates. Okay. The other thing to keep in mind, the measurements we have are snow-covered area up top. What we're interested in is SWE on the bottom. Okay, so for a particular pixel, we've got these measurements, and I should say fractional snow-covered area in this context are coming from Landsat measurements. Okay, and so the circles here are the measurements over the ablation season. And we see that there's a mismatch between our prior estimate and our measurements, which is to be expected. And so what the blue boxes do, the Bayesian update, is it integrates that information to update our states. And so we go from the prior estimates to what we call the posterior estimates, shown here. Again, just think of two probability distributions. The red is our prior. We integrate some information. That distribution shifts usually if the mean is different, and the uncertainty may shrink. And that's what we see here. So by construct, what we hope is that our blue curve on the top should match the observations reasonably well. That's what we're designing this to do. By doing that, we're also updating everything else about our model estimates, including SWE. The question, of course, is how well does that information project? And so we've done a lot of work to validate this. I'm just going to show one schematic example here. At this pixel, we've got two types of validation: snow pillows, which have daily measurements, and snow courses, which are usually monthly measurements, that show a significantly more consistent picture with our posterior than our prior. Okay, and so at least notionally, this method has now kind of been set up. And through lots and lots of testing, it actually seems to generate improvements in going from a prior to a posterior estimate. Okay, so we've done this in a very kind of piecemeal way. It would be wonderful to say we had this vision and we were going to do this globally from the start. It never works that way, right? We have to get funding for these things. So we started in our backyard in a watershed in the Sierra Nevada, got some funding from NSF and NASA to do that. So kind of our diving into this, step one was in the Sierra Nevada. We then got some funding from the Chilean government. So we did an application in the Central Andes. In each of these steps, we've kind of improved the process and standardized it. Then NASA a few years ago had what they called the High Mountain Asia team, which was kind of a team brought together to work on High Mountain Asia topics. And so we kind of broadened the scale at which this was applied over High Mountain Asia. And then most recently, we did this over the Western US. Okay, and so we've kind of learned a lot about how to do this better and better as we've moved in these different areas. And I should say, when you're working in areas like High Mountain Asia or the Andes, it's a very different environment with very few verification data and so on. So it becomes an interesting topic as you move to different types of domains. Again, without belaboring this is just to show you we've tried to grab every bit of verification data we could, whether it be in situ or airborne, in every domain we could, to try to really exercise this to make sure we're doing well. Kind of the highlights here, you can just focus on this, is that almost everywhere we've applied this, there's a significant increase in the correlation with measurements, reduction in biases, and root mean squared differences. Okay, and so we're confident that while this estimate is certainly not perfect, it's a significant improvement over kind of the techniques that have been used before. Okay, so we can now revisit this picture we had before. So before we ask the question, how well do models estimate SWE? We looked at just these groupings here. What I'm showing here is now showing our product over the Western US in the upper left corner. And I'm also integrating a couple others that are only available over the Western US, a University of Arizona product and what's called SNODAS, both of which integrate observations that are either in situ or airborne, neither of which are used in our method. So they kind of provide a good benchmark. Okay, and so the gray bar plot is our estimate, which shows about 270 cubic kilometers climatologically over this domain. As you move to the right, you're kind of moving through these from highest resolution. So our product is on the order of 500 meters. As you move to the right, you get coarser and coarser. What we see is that there is a resolution dependence to some of this, where these next three bars are all kind of in the same ballpark, not too different than ours. And in fact, the two that have observations integrated into them, the SNODAS in purple and the U of A product in red, are very similar to ours, even though we're not using the same data they did, which is kind of an encouraging thing. And it turns out in this particular case, the ERA 5 land also does reasonably well. As you move to these coarser scale products on the far right, there's a significant underestimation, okay? And a large uncertainty. And this is important because there's been lots of papers that have been written about, very important questions like what's the future of our snow water resources? And they tend to use products that are similar to those. And so it calls into question whether we are kind of getting an accurate picture of our snow water resources going forward. If we just look at this seasonally, this is the seasonal signature. We see again, there's kind of a grouping. The black line is our product. There's a grouping of products that are similar, and then most of the others are significant underestimation. Okay, you can imagine if you're a water resources planner, what you're interested in is the peak, which is very different across products, and how quickly it melts out. Those are the two kind of things you're interested in, and you see a significant amount of variability. What about other domains outside of the Western US? So we go to the Andes, similar picture here. Again, if you squint, you see some coherence, although these coarse products start to look like there's no snow there. The Andes is this very narrow mountain range, so resolution can play a significant role. The panel on the upper left is our product, and then you have all of these other ones. The two products that I showed on the previous slide are not available globally because they rely on measurements that are only available in the Western US. And so all we have otherwise are these global products. Again, in our case, this climatological estimate is about 30 cubic kilometers of water is stored in the Andes, in the Central Andes. But across the other models, we see a significant uncertainty, from overestimates by a significant margin to underestimates by a significant margin. We see that the uncertainty across these is essentially equal to the mean. So the coefficient of variation is essentially about 100% with a significant underestimation. And again, if we look at the seasonal cycle, we see in this particular case, one of the global models, the ERA 5, does reasonably well. This did not do so well in the Western US. So there's not even kind of a consistent performance as you move around the globe. Okay, one last point, I just want to make this quickly, is that spatial patterns matter as well. So this is the Andes, just a piece of the Andes here. If you're not familiar with kind of mountain language, windward is the windward side, basically where the wind is coming from. Leeward is the opposite side. And so this is the mountain ridge of the Andes here. And in almost all cases, the windward side will get the bulk of the snowfall and therefore more SWE. Leeward gets less. And that has significant water resource implications, right? If you're a water manager in Chile, you're expecting that pattern versus Argentina, much less. So this is just an investigation we did to say how well are some of these doing, not only in the global amount of volume, but in patterns, where this ratio here is kind of the windward to leeward SWE volume ratio. So in our product, it's on the order of about 1.6 across the Andes, showing the latitudinal distribution here, SWE on either side as a function of latitude. Just picking a couple of examples, we see here of these coarse products. They show a significantly different spatial pattern. So the ratio is actually below 1, which means that they're putting too much SWE on the leeward side of the mountains. So from a water resources perspective, they're kind of, the starting point is something that doesn't quite jive with what we would expect. And there's a significant amount of overestimation in the ratio. This is not to say, not to even mention that the amounts are quite different. So if you look at the color bar numbers, those amounts are quite different, but even the spatial patterns are very different. So it's not just a matter of bias correcting these coarse products to get this higher resolution product. Okay, so quick summary of this particular part. We kind of successfully developed a method that takes advantage of this long-term record that we have of snow-covered area, and in these various geographic instances, develop multi-decade mountain SWE data sets. The method requires a retrospective method. So you need all of the snow-covered area measurements before you can back out SWE. And so this is not great for real-time prediction of SWE. And that's something that I'll talk about in the context of the next piece. Okay, so in the 10 minutes or so I have left, I just want to talk a little bit about what we've been working on lately. And this is development of a dedicated mountain SWE concept. So again, without belaboring all the details, NASA has some satellites that have dedicated funding where they say through peer review, this particular variable needs to be measured. And so we're going to fund it. And then they have another set that are up for proposed competitive proposals. Unfortunately, snow has been one of those that has always had to compete. And so most recently, there's been this NASA ESE call, which JPL approached me and we formed a team to try to tackle or design what an optimal snow water equivalent project would look like. It ends up being a whole research project in itself, kind of over multiple years. So AO here represents the announcement of opportunity. Think of this as the call for proposals here. But to put one of these two together, or one of these kind of proposals together, you have to spend a year or two prior to that getting your ducks in a row. And so this particular mission that we developed was called SnowWatch. And here's all of the team members. And some of these same ideas were developed as part of an earlier proposal, a similar NASA proposal as well. Okay, so let me kind of quickly go through this. So this is a spectrum of the microwave frequency. And different frequencies are better or worse at retrieving different variables. Okay, and so in this red box are kind of different frequencies that have some information about snow. And I should say that SnowWatch, which we were developing, there was other missions out there. Snow Globe was a similar, I shouldn't say similar, a different snow mission concept at different frequencies. And then there's a few others by the Canadian Space Agency and European Space Agency that are, again, not snow specific, but at least could provide useful information. Okay, and so this particular mission that we were using is using what's called P-band, which stands out for being a very long wavelength. So on the order of a meter in wavelength. And this has some benefits. So why did we choose that? One reason is if we could choose longer wavelengths, we would. The reason we often don't is to build an antenna and a transmitter at these wavelengths is hugely, hugely expensive, something that would blow any NASA budget out. So how could we propose this? What this involves is what's called a signal of opportunity. This is a concept that's been used elsewhere. So it turns out that the military wants to have communication globally, often in terrain that is complex and under dense forest canopies. So the military has these satellites that are called the MUOS satellites that are up in space. They've been in orbit since the late 70s that are continuously broadcasting in this wavelength. Okay, so our idea, which was very appealing to the review board, although it wasn't enough to get funded, is that let me just skip to the punchline here, is that essentially the transmitter is already built and in orbit, and that's the most expensive part. So our idea was, let's launch a few receivers that are just looking for the reflected signal and get a very cheap version of what would otherwise be a very expensive satellite. The plus side of having P-band, of course, is that it's also all weather, all terrain, and penetrates through forest canopies. Okay, I'm running a little low on time, but I just want to say that how does this method work? It's a very different method than the one I talked about. It uses what's called interferometry, which is just to say that the signal gets sent out by the transmitter. The main difference between our method and other methods is that ours has a receiver, which is different than the transmitter. So it's called a bistatic system. So the transmitter sends the signal. We have a receiver looking down, measuring the reflected signal. Many other missions just have the receiver and the transmitter on the same platform. So they're getting backscattered signal. The physics, however, is the same. As snow accumulates, two things happen. This wave gets refracted and it slows down as it passes through the snow. Both of those cause what's called a phase delay. Okay, so the difference in phase between two snapshots is proportional to how much snow there is. And so if you can measure that phase change, you could theoretically back out how much snow is. And there's a pretty well-known relationship between phase change, which is phi, and snow depth and density, which are embedded in this equation. Okay, so our idea was very kind of conceptually something like this. Use the existing transmitters, we fly some receivers, and while we don't have spaceborne observations, we have some tower estimates which show a very good relationship between these two variables. So it's a promising technique. If you combine this method, transmitters which exist, which are mostly kind of in equatorial regions looking down, transmitting, and receivers that are polar orbiting, we can get coverage like this. These kind of are individual tracks. And the nice thing here is that it covers those dark blue areas that we're most interested in for mountain SWE. Okay, so what does this look like? Again, we've got these three what are called P-band receivers in orbit, essentially like a train. They're following each other. And as the Earth rotates and they're following each other, they carve out or map out a swath, essentially. It's not quite as simple as these nice animations that NASA people put together. It looks something like this, where it's kind of little strips, where the strips is where we have data, and then there's gaps in between. But the key point here is there's a significant amount of information that could be gathered using this type of approach. Okay, and so this is launching a constellation, P-band, repeat pass, and then I don't have time to show, but part of this is we've integrated a data assimilation approach that would still use all of those methods that we've talked about before. Okay, and so the unfortunate part is these are competitive proposals. So this particular proposal was not selected. In fact, neither of the two SNO ones were selected. So we're kind of back to the drawing board in terms of still not having this optimal SNO satellite. There's a pretty high bar you have to clear to get one of these funded. This is one we kind of knew would be an issue going in, is that, for NASA is very risk averse, right? And so unless you've done sometimes decades of field experiments to kind of prove these things, they are reluctant to kind of fund something that may be a good idea, but is still kind of experimental. Okay, so let me kind of conclude and summarize some future work. So in the first part, we talked about data assimilation as providing a useful framework for extracting information, often from suboptimal measurements. We were kind of able to develop long-term mountain SWE data sets, which was our initial goal, that seemed to be a significant improvement over what we have. It was not done in a harmonized way, though. It was very piecemeal as we could chase funding. So one opportunity that's out there is developing a truly harmonized global version of this. That's something that I wrote a recent proposal. We'll see if that kind of moves forward. But snow-covered area does still have limitations. It's retrospective in nature. So for water management, it gives you kind of a picture of what's happened in the past. It's not going to give you such good real-time information. I didn't mention it, but visible near-infrared cannot see through clouds. And so in areas of the globe where it's very persistently cloudy, this method essentially won't work. And if you're in areas with heavy forest, it won't be able to see through snow very well. More recently, we spent a lot of time trying to think about how do we develop a better snow mission. So where do we go from here? The bad news, of course, is it didn't get funded. The good news is that there are several other missions that are out there, none of which are, I would say, truly optimized for snow. This Sentinel-1 is already in orbit. It's at C-band, which has issues. NISAR, which is an L-band, is about to be launched, I think in a month or two. There's another version of a L-band radar from the European Space Agency. None of these are optimal, but snow hydrologists have gotten very good at taking suboptimal data and trying to estimate what we need. So I think there's a lot of potential value in this. Okay, and so what we're going to do is take, I just got a recently funded proposal with NASA, take the methods we developed as part of the proposed mission and apply them to some of these new missions. Okay, so with that, I'm happy to take questions. I do want to acknowledge funding largely from NASA for this work, some NSF, and then in the last part of the project, JPL, I should have mentioned if I didn't already, was kind of the driver of all of the technology development of these ideas. Okay, so I will end there. Thank you.
So we can take some questions.
Thanks, Steve, for a great talk. So you showed how you had the actual on the ground measurements to validate what you're doing in the West. But I was wondering how you mentioned that you didn't have that kind of on the ground measurement to validate things in the Andes or the high mountain Asia areas that you were looking at. And so how do you know that those estimates are correct if the snow characteristics, they're either wetter, drier, the density
Yeah.
might be different? How do you know that your model really works in a place other than the
Yeah.
Mountain West and the kind of snow that's
That's a
there?
great question. Great question. So I think I've maybe misspoke. We did get a significant amount of data in the Andes. So, but that was mostly us collecting it. There's very little operational data. So the nice thing about the Western US is there's operational data that exists that we can just grab. In the Andes, we had to work hard to get it. High Mountain Asia, as much as we tried, and largely for political reasons, it's hard to get data. So we kind of have used the Andes as our very extreme environment that seems to work well as a proxy for how it would do elsewhere. We started to move into parts of Canada. Again, it'll work better in certain places than others, but it seems to be an improvement in that it constrains the observation, or it constrains the models with observations at least. But that is a big unknown. So if we could get measurements that are more directly related to SWE, that would certainly improve things.
Thank you.
Yeah.
Thank you. Thank you for the nice talk. So we in Minnesota, we measure snow. And one thing I was curious about is that there is an order of magnitude uncertainty in the density and variability of the snow, depending on the snow type. So if you go from graupels to the fluffy flakes, so where is that uncertainty kind of mapped in your approach? Because it's a lot. I mean, and there's a lot of scatter in the measurement from 100 kilograms, like 50 kilograms per cubic meter to 800 kilograms per cubic meter.
Yes.
So there is a huge uncertainty in the density of precipitation.
Yes. Yes.
So
yeah, that's a great question. So, and in retrieval algorithms, that becomes a huge issue where if maybe you're measuring something closer to snow depth, but you want SWE, you need to, in our method, it's certainly an uncertainty, but it's something that is built into our models. We're at least trying to model it, and it's uncertainty to the best that we know. So the error bars that were shown for SWE is really a culmination of all of the sources of uncertainty, some of which is density.
but there was a ground truth at some point you mentioned. So how's that estimated on the field?
So we either validate with SWE from snow pillows. So we're bypassing density. We're just measuring SWE and comparing it to the estimated SWE. In another case, we are validating against airborne snow depth estimates from LiDAR. And
But in terms of density of snow, so the snow pillar is what is that?
it measures the weight of snow. So it removes the need for density. It's just weighing how much snow is sitting on top of that pillow. So it's a very direct measurement of the snow water equivalent.
Okay.
Whereas if you take a gauge to measure the depth, then you need the density to project to the SWE.
Okay.
So we try to use SWE measurements where we have them to avoid that issue. In cases where we only have snow depth, we either have to validate our modeled snow depth versus that, or use the density to try to map the observed snow depth into SWE space.
Okay.
Yeah, but that's a great question.
Thanks.
Yeah.
I was wondering about whether your models only work if the snow goes to zero in the summer, or what if you have glaciation, permanent snow cover?
Another great question. Yes, this will work best in seasonal snow that fully disappears. So we kind of try to mask out glaciers from the start. There are, wet years where the snow doesn't disappear in some places, but it's still largely seasonal. In those cases, we kind of track that through the period where the snow is still on the ground. But that's a great observation. If snow doesn't fully disappear, this method, the snow covered area method won't work nearly as well. It's hard to resolve how much was left, in that warm season before it started to accumulate again. Yeah.
Thanks for the talk. So I was wondering, when you were using the SNOTEL data as validation, have you also assimilated the SNOTEL data to either get either better estimates or actually even try to further condition some of the parameters to try to improve land surface
Yeah,
modeling?
that's a great question. We thought long and hard about that. We have chosen not to, mainly because our goal has always been, let's develop something that we could move to high mountain Asia or the Andes and apply. So we've kind of tried to use inputs that are globally available and not constrain on observations that aren't. One of the products I mentioned, the University of Arizona product does essentially, it's not truly assimilation, but they integrate SNOTEL data directly. And so my sense is there would be some improvements. One thing we always struggle with is even in validating, SNOTEL is a 3 by 3 meter pillow.
That was actually my next
And
question.
yeah, we have a 500 meter, it's, people say it's apples to oranges. I always say it's like apples to watermelons or something. It's a very different thing. Like when they match perfectly, I'm almost more suspicious than when they are kind of consistent but different, because they're two very different things. So verification of these kind of things is itself difficult. I use verification intentionally rather than validation because it is always a bit of an apples to oranges type of comparison. So the best success we've had is these airborne measurements, which are taking LiDAR, at least giving you a map of things. So we're comparing a map, which we can aggregate to our scale, to our maps. And so we've tried to use that kind of data wherever possible because we feel like it's at least a little more consistent.
I almost wonder if like bringing in discharge data or something, which on a mass balance.
Yeah, we've tried that too. And it's interesting. So we see some ability to better estimate that. And that's something we should do more of. But there's, of course, lots of uncertainties in that too. What happens between the water melting and seeing it downstream somewhere. But that's another technique that we've tried as well.
Maybe the last question from me. Are you guys using a hydrologic modeling between the map between a snow cover fraction and sweep? When you guys do data assimilation, is there any physical modeling between?
Yes.
Okay.
It's very physical, but it's a land surface model. So it's kind of the soil and snowpack.
Okay.
We have thought about trying to then plug that into a hydrologic model that takes the water and moves it downstream. So far, we've only done very little work on that. So it's physically based, but it's kind of just the surface and up.
Oh, got it. Thank you. Any other question? All right. Thank you so
All right.
much,
Thank you very
Steve, for
much.
taking the time.